Hi, welcome to today's maths class. This is our last one of the semester. So thanks for coming. Thanks for sticking with it as we've gone through. And today we're going to look through some examples to correspond to the last set of mini lectures we've done. And what we've been doing the last week is, in those lectures, is bringing together some of the different basics that we've reviewed, revised, and introduced, and looking at how we can apply those to decision-making situations where we can either test one hypothesis against another, or we can try and decide whether a model is suitable for some data. We can try and decide whether one set of data is drawn from the same population as another set of data, or whether they are likely to be separate and different. So we've got a reasonable grasp of the basics, and we've got some tools and techniques at our disposal now, which we can use for practical application. And obviously, as we're engineers, we're interested in making engineering decisions about them and interpreting data from engineering situations. So what we're going to do today is look at some more examples which came out of the work that I was presenting at the face-to-face class last week. So for those of you who weren't at the face-to-face class last week, there was a video of that on Blackboard, and that's there for you to view. So I'm just going to revise that in a moment. A few bits of business first of all. So we have released the coursework marks for the Excel questions that we set you, and they're for you to view on Blackboard. And each of you has a file that was uploaded, and that includes both some model answers and a mark scheme, and it includes some personalized feedback for you on a separate worksheet. So you can look at that, you can see your scores, and you can see where there's room to improve. I've received a number of emails from people who are asking questions about their scores. And if you believe that the mark scheme wasn't followed correctly, if there was an error in how it was applied, then I can review that. The overall average for the coursework was 74%. And you should know that for modules, we have a target average of about 65% that we aim for every year with our modules. And that gives a suitable distribution of marks so that people get firsts and 2-1s, thirds, and so on in appropriate distributions. So with an average of 74%, you on average did well and didn't find it too challenging, and found that the distribution of marks was good. So I was happy with that. I thought it went well. Some learning points about how to present data, ensuring that you use units, presenting data to a suitable or specified number of significant figures or decimal places, and so on. So some learning points. Next week, we have the online test. Now, that was scheduled for tomorrow, but we sent out messages saying that that has been postponed 1 week due to the student travel window that was introduced. So we didn't want to have an online test whilst people might be traveling. So that was put back to Wednesday next week, the 16th. This will be an online test where you have, nominally it's an hour, so we'll give you more than an hour to accommodate any problems getting yourself set up or technical issues. So we'll probably give you 75 minutes to do a test, which is nominally should take an hour. And it will be 10 questions on Blackboard as a quiz format, which may be multiple choice, or they may require numerical answers, and for you to do some working, and then you input your answer into Blackboard. We're going to send full details of that around later this week to explain how that will work. And then next year, in the beginning of next year, in January, there'll be a written exam that you do. And that exam, which is worth 50% of the module credit, will be based, both next week's test and the written exam after Christmas will be based on all of the work that we've covered in the module over the whole semester with Dr. Abdul and myself. And the exam after Christmas will consist of 2 questions, one generally on Dr. Abdul's stuff, one generally on my material. And you will, again, normally have an hour to do it. So each question is normally 30 minutes, and you'll have more than that time to do it, again, to accommodate any time for technical issues, doing an online test and accessing the material and uploading it and so on. That will require you to download a PDF to write your answers and solutions, which you can do on pen and paper if you choose to, or you can do it on a computer if you choose to. And then to upload, take a photo of that, or however, by whatever means, upload your solutions onto Blackboard after the allotted time. So I'm looking at the chat. Do we need to know explicitly the derivation of the linear regression expressions to find alpha and beta? Well, I don't expect you to memorize those equations, but I expect you to understand and to be able to derive the method for it. You need to be able to follow the method. So that requires you to know what the function is that you're trying to minimize. And then you'd have to be able to do the partial derivatives to minimize that and work through the algebra to derive those expressions yourself. What topics will be on the 20% assessment next week? That's all the topics will be on that. Are there 2 questions for the test next week? No, next week there will be 10 questions. Each question is worth 2 marks. The 20% exam is a PDF we need to download. No, next week's exam is 20% credit, and that will be a Blackboard test. So you go into Blackboard, you open a test or quiz, and it gives you a series of questions that you answer in the allotted time. And the syllabus for the test next week is all the material that we've done in the module so far. Okay, so I've answered the questions that have come up on the chat about those assessments. Including week 10? Yes, including week 10, all of it. Any more questions? Don't see any more. Okay. So I'm just going to show a couple pictures from the presentation that I tried to give at the face-to-face session, and which is in the online recording for the face-to-face session. Those of you who were at the session know that the audio-visual stuff didn't work on the day, sadly. So I can show you this if you've not seen it. This is just an example experiment where which I've worked on in the past, and we can use it to illustrate the application of some of the techniques that we've seen so far. This is a lump of bread dough, and this is something that we were studying at the time, and we were looking at the bubble structure of the bread dough. You can see the bubbles here when it's open, and these bubbles grow into the final loaf of bread, and so it's something you can try and manipulate to control the quality of bread or to adjust the nature of the bread and the manufacturing process. And so the particular experiment we were doing is we were making a dough, and then we were cutting lumps out of it, a few centimeter cubed lumps, and we wanted to know how much gas within the dough. So what's the total volume of gas bubbles per volume of dough in the dough. So I'm going to skip the parts about how we did that. Just to show you this. So when we wanted to measure the amount of gas in the dough, we call that the dough voidage. We can do that accurately by means of weighing the dough piece in 2 different fluids. And obviously the weight of the object is a combination of its mass and of its buoyancy in the whichever fluid it's in, and obviously gravity and so on. And so when you weigh it in air, then the buoyancy force due to the air is very small. But here we're weighing it again in xylene. And so there's a buoyancy force, and the buoyancy force is proportional to or equal to the density of the xylene multiplied by the volume of the sample. And so by measuring these two different weights and different fluids, we're capturing what the volume of the sample is in a much more accurate way than we can do by trying to measure it in any sort of visual way. So you have two measurements. The mass, we measure it as mass because that's what the scale, the balance gives us. Mass in air, mass in xylene. And then the third thing we need to know is what's the density of the xylene. So we have a number for the density of the xylene. And we are trying to calculate from that what the density of the dough piece is. And then ultimately we're trying to send that to the back, we can see it. So we're looking at data which shows us a range of mixing pressures. So we're doing this experiment at different experimental conditions. So we change the pressure in the mixer. This is the dough density as we take it out of the mixer. And you can see it changes. And what we're interested in is both studying how this dough density is changing with our process parameter, mixer pressure. And then ultimately we want to calculate dough voidage. That means the amount of gas in the dough. And that's equal to 1 minus the density divided by the gas-free dough density. And that gas-free dough density means the density of the dough if it had no bubbles of air in it, no bubbles of gas in it at all. So we want a value for the gas-free dough density. And one way of getting that is to look at this. Well, we've got a mixer pressure scale here. And if you mixed under a complete vacuum, there would be no gas in the dough. There'd be no molecules of gas in the dough. So any voids in the dough, as soon as you take it to atmospheric pressure, they will collapse because there's no molecules in them. And you'd have a lump of dough with absolutely no gas in it. And so a way of getting this rho GF number is to extrapolate back on this line to pressure equals 0. So we did an experiment close to that point, as close as we could. It's quite hard to pull a very big vacuum. These are both under partial vacuum. So you can extrapolate back. And if you have a confidence in the model that you're using, then we have reason here to then extrapolate outside the range we did the experiments to 0. So what we're trying to do with our data is to assess each of these data points and consider what the nature of those are, assess this correlation that we have of the data as it changes density, as it changes with pressure, to look at the fitting of the straight line and to look at how confident we are with that. And to look at this value rho GF, that's something we're trying to calculate from our data, but we'd also like to know what the confidence of that value is. We know that we can extrapolate a line and look where it passes through the y-axis, but we'd also like to have some knowledge of the confidence of that number, or what the expected uncertainty is in that value. So there's a few practical things that we'd like to extract from our data. So that's the objective of it. So I'm going to talk you through how we can do that with that data, and that will illustrate the application of a few of the techniques we've had. I think there was one more slide just to this one. So this is just to remind us of the equation for finding that density. So we're interested in the dough density rho, and that's equal to the density of the liquid xylene multiplied by the mass of the sample in air divided by the mass in air minus the mass in xylene. And what we did in the face-to-face class was we looked at the data we'd measured for these, and we looked at the error propagation through that, so that for each sample we took, we could look at the errors in the measurements and then calculate the expected error in the calculated value of density. So that's what we got, and I'll just show this one again. So I showed you some of this data during the face-to-face class and its video, or in the video of the class. And you can see we collected data, so we've done different runs, and you can see each run is with a different pressure in the mixer. So that's our variable that we're looking for a trend with. Each time we've done a run here, we have taken 6 samples of our dough, and here are 6 pairs of numbers: mass in air 1, mass in xylene 1, and so on, 2, 3, 4, 5, 6. So we had the lump of dough, and we took 6 lumps, some smaller samples out of that dough and measured the pairs of masses for each one. So the conclusion of what we saw in the face-to-face class was that we could identify the starting point errors. So we took this as the accuracy of the balance. We took this as the accuracy of our dough, so of our xylene density. And then we could work through the contributions to the overall accuracy. And we found that the propagated error of our density measurement based on our presumed accuracy of the measurements was about 2 × 10⁻⁴ grams per centimeter squared. So that was the main outcome of that. But we then compared that. So we've done 6 samples from our lump of dough. We took 6 different pieces and we measured them individually. So we have 6 measurements of dough density from one overall experiment. And if you look at the variance of those 6, or the standard deviation of those 6, we have a number of 3 × 10⁻⁵. And so immediately you see that the variance here, or the standard deviation here, is an order of magnitude larger than the standard deviation here based on propagated error. So immediately it's apparent that the propagated error of the measurements, the errors that we've identified, is not going to be responsible for the variance in the data over the 6 samples we've measured. So that tells us that there's some other aspect of the experiment which we haven't controlled. There's an unidentified error or inconsistency in the experiment. And so it means that there's not much point using this value of propagated error for anything else, because this one, the actual standard deviation of our 6 measurements, is going to be more representative of actually how much variance there is in measurements of a single experiment than by looking at the propagated error. So that's the first thing we saw, is it's really important to do repeats of experiments. Don't rely on some error propagation calculation, because you might well not have identified all of the variables which are happening from one run to another. Okay. So I'm going to stop showing that screen. And just write down a few bits here. So what we're doing is we're looking at this plot of pressure against density, and we saw we've got some data points. And we're trying to find this value, rho GF here. That's something we'd like to find so that we can use it in our equation like that. So we've got something we want to use it for. We've already looked at this calculation of rho. We did that before. And we did the error propagation. We used a value of xylene density. And we remembered the propagation of error general equation, where you take the partial derivative of your function with respect to each variable, and square that and multiply that by the variance of each variable, add them up. And when we did that, what we found was that the propagated error for one of our samples, just looked at one of those pairs of measurements, was of the order of 2 × 10⁻⁴, whereas the variance, or the standard deviation of our 6 different samples, so from row 1 to row 6, was 0.00319. And so this is the important one. It's much bigger than that. So there's uncertainty in our experiment. So why is that? So from an experimental point of view, this number is not necessarily unacceptable. It's quite good. But what is it that's varying that we haven't captured in this? So that's a worthwhile thing to think about. And so then you have to sort of think about your experimental method and what you're doing. And so we need to think about that and try and identify what might be going on. So the first thing to note is we have one large lump of dough that's come out of a mixer, and we're taking 6 different samples from it, and we take those from different points of the dough, and we try and disperse them randomly over the whole volume. And so taking it from different regions is going to be a worthwhile thing to do, because it is making sure that if there's any distribution of bubbles within the actual lump of dough, we're going to get them from all regions and sample them. So any distribution of bubbles within the dough is actually a legitimate reason why we're getting this value here. This is capturing something about actually how inconsistent the dough voidage might be, or the dough density might be within the actual lump of dough that's come out of the mixer. So this doesn't need to be an error as such, it's just actually measuring an attribute of how the thing we're measuring varies throughout the dough. But other reasons it might vary, if we were doing one experiment to another, it could be due to different ingredients, different amounts of ingredients in particular. If we were repeating the actual run, this data actually came from just one lump of dough. We didn't repeat the run each time. If you were doing repeats each time, you could get different pressures, some difference in the mixer pressure. The time that you mix it for could vary a little from run to run. The speed the mixer runs at could vary from run to run. So these are all random errors that could get into your experiment. But there are also systematic errors that could get in. So for example, temperature could be one of those. So if the temperature in the lab is changing throughout the day, if it's getting warmer through the day, that's going to affect the temperature of the ingredients, and that will affect the temperature of the dough that you've made, and that will affect its rheology, and that will affect the way it's mixed, and will affect the amount of gas in it and the density of it. So when you have a systematic error, that again could occur throughout the whole mix, throughout the whole day, and affect the results. So one point for you to note, if I show you how you did this experiment, if you look at the, here we have the run number, so that's the sequence we went through when we did the experiment. So a good starting point for any experimental design that you do, like in the second year, you're going to design your own experiments in labs, is first of all to randomize the variables that you're changing. You're controlling the pressure of the mix, and so don't do it in order, like smallest to largest, because then any systematic errors that are present are more likely to manifest themselves through the course of the day and affect your data. And it might make it look like there's a trend when there isn't one. And so by randomizing the variables that you do is a good way of minimizing the effect of systematic errors. Okay, so that's where we're at with that. What we want to do now is to look more closely at this data, given the uncertainty that we can use for it, and look at how we can apply some of our techniques. Okay, so if we take 2 data points, we're actually going to take these first 2. The first thing that we might ask ourselves is, well, we're saying that there's a difference between these. We're plotting a line through it, but how could we be sure? We've got a mean value of density, and we've got an uncertainty associated with each of these points. We've got a different mean and a different uncertainty. Each of these is based on 6 measurements, so we've got a separate variance for each of them. How sure can we be that these are actually representative of samples from 2 different populations, rather than actually that they're both samples from the same population? So if actually there isn't a trend in density here with pressure, the density is always going to be about the same. There's just some random difference between 2 different samples that were taken. So how can we assess that? That's our first question that we want to do. So is sample 1A different from 2A? We want to check that we can answer that. And so if we just write down what our values are. So the mean density for 1A was 1.15461, and the standard deviation and for 2A we have these numbers. Okay, so we've got two means and two standard deviations, and so we can apply a hypothesis to this to answer our question. So the hypothesis is that if we take the difference between the two populations, that the mean of those would be equal to 0. So we're hypothesizing that, okay, well, if the populations that these two samples are from, there's population 1 and there's population 2, and we're hypothesizing that these are from the same population, and therefore the difference in means of the two things is 0. And then the alternative hypothesis is that the difference between them is not equal to 0. And so this means that our samples are taken from the same population, and we want to have, let's say we want a 5% significance level. For our test, and it's going to be two-tailed because this difference here could be either greater than 0 or less than 0. So we're going to use the two-tailed condition for that. And we've done this in the mini lectures, but just to clarify what we're doing, if you have two samples, A and B, what we're doing here is we're looking at what happens if you take the distribution of one away from the other. So we're saying we're taking the difference between A and B, our samples, and the properties of normal distributions that we're using work out such that the mean of C is equal to the mean of A minus the mean of B, and the standard deviation of C is equal to the standard deviation of A plus the standard deviation of B square rooted. So those are things that come out of linear operations on the normal distribution, which are similar to what we did in the mini lectures, although I don't think we did that one specifically. But then we can use that result to work out what the properties of our combined population is. So we're taking our two samples, we're subtracting one from the other, and we want to test this hypothesis. So to test it, we need two things. We need our value of Z. And so our value of Z we get from our data and by scaling that in the way that we showed in the mini lectures. Each of our samples has a standard error associated with it, and that standard error is the standard deviation of the distribution of the mean, and so that's the relevant standard deviation to use for our test. And we square root all of that like so, and that's going to give us our Z value, and so that's going to be equal to 1.15461 minus 1.24404, and that difference is 0 for H0. Okay, so we work out that value of Z, and I got minus 68.6. And then we look at our tables to find this. So I'm going to show you, I used some different tables previously, I'll show you this one. So if you were doing an exam in Manchester, this is what you would get with your exam. It's a set of standard mathematical formula tables, and a copy of this is included on the Blackboard webpage for our module. And it contains various useful stuff, and we're just looking at the distributions that are in here. So here's the normal distribution. Okay, so this shows us what the cumulative distribution function is of the standard deviation of mean zero, sorry, of a normal distribution with mean zero, standard deviation of 1. And we have a two-tailed test at 5% significance. That means we're looking for a value of 0.975. So here we go, that's this value here. You can see that, that's 0.975. And then we can read off what our value of Z is from that. So here we have 1.9, and then this tells us it's 1.96. This tells us what the second decimal value is. So our Z is equal to 1.96. It's a two-tailed test that we're doing. So we're interested in both of these regions if our result is in either of those. And so our Z is at minus 68. Our criteria is at plus or minus 1.96. And so you can see that our data is way outside of the 95% of the data. And so H0 is rejected. And so therefore, these two samples have not come from the same population. We've proved that we're more than 5% confident of that. And obviously there's a huge difference here. And so we could apply a more stringent test as well if we wanted to improve that we're more than 99% confident and so on. So we've done the first thing, which is no surprise, but is good. We've looked at two of our data points and proved that they are not from the, or unlikely to be from the same population. So there is a difference. As we change the pressure of the mixer, it is making a difference to our dough density. So that's the first thing we've checked. The second thing we can check is whether there's a correlation. So this is obviously going along the similar lines. We've got pressure, we've got density, but we've obviously got more than two data points. So rather than checking each pair of them and so on to see if there's a difference between them, instead what we do is we look at whether there's a correlation here. And we know that we can use the parameter R, that's the coefficient of correlation. That's a parameter that we can use to describe how much correlation there is between some data. R is defined in the mini lectures, and you've encountered it many times already, I expect. Sorry, I was just double checking this because I thought I'd made a typo. I might have made a typo. I can't tell on that one. Let me just check on the lecture notes. Yep. Sorry, that should be a 1, not an N. Okay, so we've got our value for the correlation coefficients. That part of it is called the covariance, and then we divide that by the product of the standard deviations of our x variable, it's the non-biased version, and our y variable, it's a non-biased version, like that. That's what you're familiar with. That's a number between -1 and 1, and tells us about the nature of the correlation. But it doesn't tell us whether or not there is a correlation in any statistical sense. And so to find out if there is a correlation, we have to apply a test. And so the test involves us calculating a different parameter, a test parameter, r test, which is equal to the modulus of r n minus 2 divided by 1 minus r squared. And this is a t-test, or t-distribution that we will do to it. So what we're going to look at is a hypothesis. And what you're hypothesizing is that the coefficient of correlation of the actual population that this data came from is 0. So we're going to call that rho equals 0. Rho to distinguish it from R. R is based on the actual measured data. Rho is the population that our measured data was sampled from. And obviously the alternative hypothesis is that, the alternative hypothesis is that rho is not equal to 0. So again, it's two-tailed. It's a t-distribution. And the degrees of freedom is n minus 2. So we can find our value for the critical R from our tables. So this is the t-distribution from our tables. We're looking for, it's two-tailed, with 5% confidence, we're looking for 0.975 with n minus 2. N was the number of samples, which was 6. So 6 minus 2 is 4. That's our degrees of freedom. So that's 2.776. So that's our test value. And if we work out our value for our test from the data, first of all, if we look at what R is equal to minus 0.998812, something like that. And our test was equal to 40.99. And so obviously our test is greater than our critical value. And so H0 is rejected. And so here we've proved that for all of this data set that we've got that, that there is a statistically significant correlation between them. So that's good. So that's illustrating how we can use another of our tests to look at some data. Then the final thing we wanted to do was to fit a line to this. So we're going to say we can fit a straight line to it. And in particular, we want to find this value here, the intercept, which is we call the gas-free dou density, because that's something we want to use. And we'd like to not just find the most likely intercept, we'd like to find what the uncertainty in that is, have some measure of the uncertainty in it. So again, we can follow a method that we did in the mini lectures. And for our data, we've got separate values of variance for each data point. And so you can either do, you could do some variant of least squares fitting. In the mini lectures, I introduced the chi-squared parameter. And this is where we look at the difference between the measured value and the predicted value. And we include our separate values of sigma I, and we square that. So this is, well, it's the same as the least squares method. If you look through the derivation using the maximum likelihood estimate, this is where we started from in our probability distribution function setup. For the ordinary least squares, we assumed that this sigma was constant, and we took it outside the summation. So that's the ordinary least squares that you'll have seen before, probably. But if this is not constant, or if we don't have to assume it's constant, and here we have different values of sigma for each data point, then we can incorporate that as well. And that's going to give us a better fit. And so, for example, you can imagine one effect of that is that if you have a data point where the error was larger than the others for some reason, so we have a higher uncertainty in one data point than the others, this is going to have the effect here that it has a lower weighting on the overall sum. So the larger the error, or the larger the uncertainty, the lower weighting that data point has in the overall sum. So it makes sense as well as being mathematically sound. And then using that method, we found that we can calculate our parameters. So the rho GF, that's the intercept, which we called alpha in the mini lectures. And alpha was equal to SSX SY minus SXY SX divided by SSX X minus SX squared, like that. And that's the same result that you've seen before. The definition of those summations just includes that 1 over standard deviation term. So that's something that you can derive by starting with this type of summation and then doing the partial derivatives with respect to alpha and beta to minimize it. You can then get a pair of simultaneous equations, and you can work out that that's what alpha is, and you can work out what beta is. And now that we've got an expression for alpha, we can use the propagation of errors technique on this equation here. And so you know the errors for those, and you can then find the propagated error for alpha. So this is the standard deviation of the gas-free dye density, and the expression for that we derived in the notes was SXX over SXX minus SX squared, like that. So using propagation of error on this means that we can find then a measure of the uncertainty in this intercept. So for our case, when we did that, we got values for the gas-free density of 1.249 grams per centimeter cubed, and the uncertainty in that was 0.0013 grams per centimeter cubed. So that's really useful. We've extracted from our experiment a useful parameter. We can then use that further for more analysis, and we've also got an uncertainty associated with that value. And of course, there's quite a few assumptions that have gone into this. We've assumed random errors, we've assumed independent errors, we've assumed that there's enough of them that they are normally distributed. But with all of those, we can still estimate what the significance of that is. And you can see that this value is we can compare that to what we had at the beginning. So our initial uncertainties in each of the measurements were of the order of 0.003 or 0.002. And you see actually the uncertainty in this value is lower than the uncertainties of the individual values. And that's because we have all of the individual values that we're plotting the line through. And so that adds to our confidence. So the overall uncertainty from that analysis is actually less than the uncertainty of the individual data points that we extracted it from. Okay, so I think I'll leave it there for that one. We have seen how all of the maths that we've been using can be applied in a practical sense to experiments, and that's really the emphasis of this module, is to help you through your design projects and your experiments in second year labs and first year labs, and research projects in the fourth year, industrial placements, all those things. You're equipped with the basic concepts that you can understand the data that you're presented with, understand how to design an experiment to get some data, and then understand how to use that data to make reliable conclusions and reliable models of what's going on. So thank you very much for listening, and thanks for your participation in the module this semester. Like I said, we'll put the details of the online test available this week, so you can see what's going to be in that. Your classes, the individual classes will start now. Vishnu's not available today, and so he asked if you were in his group, whether you can join one of the other groups today. So I will just get you details of a different group you can join if you don't have it already. So I've just added onto the chat a group for Dan that you can join. If you're in Vishnu's group, please join this group instead, and you'll be able to talk to them about your questions and your solutions. Yes, this is our last synchronous session